Okay, so let's start with this one. We have to start by calculating those external loads. And to some degree, what these external loads are depends on your interpretation of what these joints can do. I'm going to treat it as that pin joint keeps this thing from rotating, like barrel rolling. You know what I mean? And so I'm going to apply a reaction torque at the left end where that pin joint is. And I'm not going to assume that that roller can prevent rotation. So I'm not going to apply an external torque there. So I'll have an unknown force R here and an unknown torque, fancy TR. And then at the midpoint, I'll call this RA and I'll call this one RB. And then we'll have that applied given torque of 1500. And 5,000, 3,000, and then the 2,000. Okay, and I'm going to put my about point here. So Newton's second law says RAX RAY plus 0, negative 2,000 plus negative 5,000, 0 plus 0 RB. 1, 2, 3, 4 is equal to 0. So right away we know that RAX is equal to 5,000. And then the moment equation about the z-axis. So we have plus or minus for the 2,000. Let's see. So the whole thing is 2 meters long. So it's 1 meter to there, so 0.5 meters. So the moment arm for the 2,000 Newton force is 0.5. And with the about point at the red dot, the 2,000 would make this rotate clockwise. So I'm going to take the negative. And then we have plus or minus a moment arm of 1 and a force of RB. And that would make it rotate counterclockwise. So I'll take the positive. And so we get that RB is equal to 1,000. And then I can use that to calculate RAY. So RAY is positive 1,000. And then the moment equation about the x-axis. We have fancy TR. 1,500 in the positive direction, so plus 1,500. And then the 3,000 is in the negative x direction, so minus 3,000 is equal to 0. So TR is equal to positive 1,500 Newton meters. Any questions about the external forces or the external loads? I guess that couple is not a force, but it is a load. Now we can do our cuts. So how many places are there in between the endpoints that are going to add a new cut to this? Yeah, 2. So if you start with 1 cut, we have 2 more, so 3 total cuts. So my first one is going to be for x values between 0 and 0.5. So cut 1 is for x's between 0 and 0.5. And so my free body is going to be from all the way at the left to some distance x that's between 0 and 0.5. And we know that we have a 1,000 here. We have a 5,000 here. And we have a torque of 1,500. And we haven't gotten to the 2,000 yet. And then we have our internal loads, T, V, M, and fancy T. And I'm going to do my moments about the left endpoint. So Newton's second law says 5,000, I'll combine these 2 force components. So 5,000 x, 1,000 y, plus t negative v is equal to zeros. So t is negative 5,000 and v is positive 1,000. So for this part, is this beam in tension or compression? Compression, because the t value is negative. And then the moment equation about the z-axis. The 1,000 doesn't do anything. All we have producing moments about the z-axis with the about point at the red dot is m minus vx is equal to 0. So m is equal to vx. Substitute in 1,000 for v, and you get that m is equal to 1,000x. And then the moment equation about the x-axis. We have positive 1,500 plus fancy t is equal to 0. So fancy t is equal to negative 1,500 Newton meters.
Right, so what is fancy T again?
That is the torque that's applied to our piece by the adjacent material. So
represents
you could use the right-hand rule, and what that's saying is the material that's missing here is if T is positive, it's trying to twist this end of the material this way. And we got a negative value, so it's in the opposite direction, so it's trying to twist it this way. And it's doing that to counteract this 1,500, because otherwise this piece would have an angular acceleration. Okay, and all these are valid on the interval where x is between 0 and 0.5. So we're getting this piecewise function, and that's like the first piece of our function for all of those. And now we'll go to cut 2. So this is for x values between 0.5 and 1. So we have our 1,000 force and our 5,000 force and our torque of 1,500 and our 2,000 Newton force down. But we haven't gotten to the roller or that applied torque. And so the only other forces, loads, are the internal tension, internal shear force, internal bending moment, and the internal torque. So Newton's second law says 5,000, 1,000 plus 0, negative 2,000 plus t, negative v is equal to zeros. So t is still equal to 5,000. V is equal to negative 1,000.
Wait, what EV was negative 5?
Yep, thank you. And then rotational Newton's second law about the z-axis. My about point is still going to be here. So we have plus or minus moment arm of 0.5, force of 2,000. That would make it rotate clockwise, so that's negative. And then we have plus m minus vx is equal to 0. So m is equal to vx plus 1,000. Substitute in negative 1,000 for v, and you get m is equal to negative 1,000 x plus 1,000. And then the moment equation about the x-axis. Uh, 1,500, and then the only other torque is the internal torque. So fancy T is negative 1,500 Newton meters. And these are valid for x's between 0.5 and 1. And then the only other cut is when the right end is between the roller and the end point. So cut 3 is for x's between 1 and 2. So we have the 2,000 Newton force, and we have the roller force of 1,000 that we had to calculate, and we have the externally applied torque of 1,500. And then we have our upward force of 1,000 at the left end, and our 5,000 Newton force at the left end, and our couple, our torque of 1,500. Those are all the external loads. And then our internal loads are T, V, M, and torque. So Newton's second law says 5,000, 1,000 plus 0, negative 2,000 plus 0, 1,000 plus T negative V is equal to zeros. So T is equal to negative 5,000 newtons. V is equal to 0. And then the moment equation about the z-axis with the about point at the red dot. We have plus or minus moment arm of 0.5, force of 2,000. And that is a clockwise moment. Then we have plus or minus a moment arm of 1 and a force of 1,000. And that is a 2,000. Oh, yeah. Where's the... so that is a counterclockwise rotation, so that's positive. Then we have plus m minus vx is equal to 0. So m is equal to, the 1,000s cancel out, and you just get m is equal to vx. V is equal to 0, so m is equal to 0. And then the moment equation about the x-axis, you have 1,500 plus the new 1,500 for this cut, plus the internal torque is equal to 0. So the internal torque is negative 3,000. And all this is valid for x values between 1 and 2. Any questions about that? Okay, so the next thing that we're going to do is we're going to take these internal loads and beams, and we're going to learn how to figure out what the stresses are at various points in the beams due to these internal loads. So before I go on, any Anybody want to see any other of those internal load calculations? Any of the homework problems besides number 3? Yep.
Can you just show us what the T, V, and M diagrams are?
Oh yeah, that's just graphing out these piecewise functions. So okay, so as a function of x, uh, t just stays at negative 5,000. So that looks like this. V goes, so it starts out at positive 1,000, then it goes to negative 1,000, and then it goes to 0. So um, so it starts out like this, then it does this, and then it does this. And people connect those with lines, which doesn't make any mathematical sense, but it does make a little bit of sort of understanding sense for what's going on in the engineering, because there really aren't such thing as point loads ever. Loads are always distributed some amount, and so that just sort of represents what would be just sort of a steep slope in the real graph. And then the bending moment, so that starts out at positive 1000x and goes to a value of 500. Then it goes back to 0, and then it stays 0. So this looks something like this. And then for the torque, the internal torque, negative 1500, and then negative 3000. So that goes like that. Any questions about any of those graphs? I make you do a few of those on homework, but I'll never make you do those on tests. It's just graphing stuff. So I assume you know the URL for Desmos. Want to see any other of the homework questions? Okay, so now we're going to get into calculating stress tensors. So now.
Did you say what the exam's going to be up through?
Oh, I did not. So the exam is a week from today. And oh, right, I did not even, I never have said that, but I can tell you right now. Let me think. So before internal loads, so it's going to be everything up through stresses in pure tension compression, or bodies in pure tension compression, or whatever that's called. So it's going to include It's going to include pressure vessels, trusses, and then everything before that. Okay, so now what we're going to do is calculating stress tensors at a point caused by internal loads. Um, and all of this is going to depend on what's called the superposition principle. And that says that for small deformations, the stress due to internal tension, shear force, bending moment, and torque can be calculated as first determining a stress due to internal tension and assume that's the only internal load. Then calculate the stress due to shear force and assume that's the only internal load. Then calculate the stress due to the bending moment. All of these are tensors. Assume that's the only internal load. Then do it for the internal torque. Assume that's the only internal load. And then the total stress tensor is just the stress tensor you got for internal tension plus the stress tensor you got for internal shear force plus the stress tensor you got for internal bending moment plus the stress tensor you got for internal torque. Okay, so the fact that we're dealing with small deformations means that we can calculate these one by one and then just add them together. What does it mean to add stress tensors?
They're matrices, so is that together a set of matrices?
Yep, so you're just adding element by element. So for example, if you had a matrix, let's say 5, 0, -1, 0, 2, 0. I'm going to make these symmetric, but this is true of adding any matrices. -1, 0, -4. And you're adding it to the matrix 0, 2, -1, 2, 0, 5, -1, 5, 10. The sum of those two matrices is 5 plus 0 is 5. 0 plus 2 is 2. -1 plus -1 is -2. 2, 2, 5, -2, 5, 6. And notice that if you add two symmetric matrices, you get a symmetric matrix back. Okay, so this is a valid stress tensor. And we are always going to use this coordinate system for our beams. So if this is our beam from the side, as we're doing the calculation, we're always going to have the x-axis pointing along the beam's axis, the y-axis pointing up, and the z-axis coming out towards us. We're also going to often think about cross sections of the beam as we do this. So I want you to think about what a cross section would look like. We're always going to think about the cross sections like looking at it from here, like the beam is pointing into our eye. Okay. So the cross section that we'll see will look like this. So, well, it won't always be rectangular, but the axis directions will always be the same. So the y-axis goes up. Which way does the x-axis go, left or right? No, the x-axis doesn't go left or right. That was a trick question. The x-axis goes like into our eye. Which way does the z-axis go, left or right? Left. Okay, so we're going to get used to this coordinate system. That's always how we're going to describe these values. And we're going to start with the easiest one. So, we have 1, 2, 3, 4 different topics. One for calculating stress due to internal tension, shear force, bending moment, and torque. And the easiest one and the first one is the stress tensor due to internal tension. And one thing that's important about this is there are no requirements about the shape of the beam. This is the only one of these stress tensors that's going to have no beam requirements. So these, talking about the beam requirements, will be a big deal for the other internal loads. And one thing I want you to notice on all of these is so for the stress values from each individual internal load. You can trust the signs that come out of the equations. So if your internal tension comes out as negative 500, you can plug that negative 500 into the formula, and you can just trust the sign that comes out of that formula for your stress element. Okay? That's not always true in engineering, but it's true here. And so now we can get to, and it's basically, this is a one-line section, and it just says, what's the stress tensor due to internal tension? The only non-zero value is the X normal stress, and it's equal to the internal torque over A, where A is the cross-sectional area. Okay, so let me do a simple example. Let's say we have a cantilever beam. And let's say at the midpoint, we have a force going this way of 500 newtons. And at the end, we have a force going this way of 1200 newtons. Let's make the length of this 0.4 meters and the length of this 0.8 meters. And I'll put another load in here just so you can see that the way these work together. Let's call this 3,000 newtons. And then let's say the beam's cross-sectional area, or the cross-section, let's say we have 0.01 meters that way and 0.02 meters that way. So this beam is 1 centimeter across, 2 centimeters tall. And we want to calculate the stress tensor due to internal tension. Okay, well, first we have to calculate the external loads normally in order to calculate the internal loads. In this case, since the only external loads that we aren't given are at the right end, we can skip that and we can just go right into the cuts. How many cuts are there for this? Two, yep. So cut 1 is going to be for X values between 0 and 0.4. And we have a 1200 Newton force there, a 3000 Newton force there. And then our internal loads, T, V, M, and torque. All we care about is the internal tension, so all we're going to use is Newton's second law. we have the negative 1200, negative 3000, plus t negative v is equal to zeros. So t is equal to 1200. And that is for all the x's from 0 to 0.4. And then we'll do our second cut. So this is for x's from 0.4 to 0.8. We have our 1200, our 3000, and then we have our 500, and our internal loads. So Newton's second law says negative 1200, negative 3000, plus 500, 0, plus t negative v is equal to zeros. So t is equal to 700. And this is for all the x's from 0.4 to 0.8. And so now on the first half, from 0 to 0.4, we have that sigma xx is equal to an internal tension of 1200 divided by the cross-sectional area. So that's 6.0 times 10 to the 6 pascals. So the stress tensor due to internal tension is 6 times 10 to the 6 and zeros everywhere else. Okay, and if you wanted to draw the stress cube, it would just be this. Okay. Is this in tension or compression?
Tension.
Tension. So because that T was positive, and you can see from the stress cube, it looks like you would expect it to look. If you have a positive value of internal tension, you have a positive value of normal stress in the x direction. If you have a negative value of internal tension, you have a negative stress value. Okay, and then for the other half, so now for x values between 0.4 and 0.8, sigma xx is equal to positive 700 divided by 0.01 times 0.02 So that is 3.5 times 10 to the 6 pascals. And so the stress tensor due to internal tension is 3.5 times 10 to the 6 and zeros everywhere else. Okay. So is this half in tension or compression? Tension again, because it's positive. One thing I want you to notice is stress tensors represent a single point on a material. Okay, so I said that these stress tensors are valid for all x's between 0 and 0.4, and then the other one is valid for all x values between 0.4 and 0.8. But I didn't say anything about where on the cross section these are. Okay, and that's because for internal tension, the stress is the same all the way along the cross section. Okay, so notice that the stress due to tension never varies on a cross section. All the other types of stress will. Okay. So when we start talking about the stress due to bending moment and shear force and torque, where you are on the cross section at a given x value is going to change what the value of the stress is. But that's not true for this one. Okay. So the next one we're going to do is bending moment. We're kind of just going by complexity. Bless you. So the stress due to bending moment. I said that the stresses due to internal tension don't have any beam requirements. There are requirements for the beam here. So this calculation does have beam requirements. And there are 3 of them. So the first one, so these are the requirements. The first one is that the beam is straight or nearly straight. Okay, so let me just draw a picture as we go for each of these of what we can do and what we, in this class, can't do. So here we're talking about straight as you look at the side of the beam. So we can do that. Um, we can't calculate stresses in, like a hook or something. Second, the beam needs to be prismatic or nearly prismatic. So the cross sections, as the x varies, it can't change very fast as x changes. So prismatic or nearly prismatic. Prismatic means every cross section is the same. Um, so we can do this, but what we can't do is a beam with drastic changes in cross section as you go along X. And then third, the last one is the cross section has to be symmetric about the y-axis. So we could do a beam like this, which is actually a pretty, pretty complicated shape, but we could do this because the y-axis is like this and it's symmetric about that. That's y, that's z. We're looking at the cross section here, remember? But we can't do the same shape like this. So here the y-axis would be that way, the z-axis would be that way. And you might think at first, like, oh, well, why can't we just imagine we're looking at it sideways and then you change the coordinate system and then it's fine. But remember that really what these coordinate systems are defined by is the direction of the loading. We can only calculate those internal loads when the vertical forces are in the XY plane. You know what I mean? So the one on the right here that we can't do is implying that we have, like, say, downward forces bending the beam, and then we can't do that. Things get weird with the stresses. But as long as it's symmetric about that vertical axis, it's fine. So another way to say this, actually a better way to say this, is bending can only happen in the XY plane. Okay, so now we have to think about how stresses would develop in a beam when you bend it. So how do stresses develop in bending? Okay, well, imagine taking a beam like this, and we'll draw a center line here. And imagine bending it, and you would do that by applying a couple like this at one end and a couple like this at the other end. And what would happen is that this beam would deform. That's exaggerated compared to the small deformations that we can deal with, but it would do something like that. Okay. And that red center line would stay the same length. I'm doing this as if it's a sort of a thought experiment, and some of it your intuition tells you, but also this is an experimental fact. You know, if you do this bending and do these measurements very carefully, that center line stays the same length, and that's called the neutral axis. Well, we're looking at it from the side, so that's really a plane. But what does that mean for the top and the bottom? Think about like if you're in a track race, you have to do one lap around the track, and one of you is going to be on the inside lane, and one of you is going to be in the outside lane. The person on the inside lane is at a big advantage because they have a lot shorter distance to run. And so, in order for this to hold and for that red line to stay the same length, the inside lane of this bend has to get shorter and the outside has to get longer. So, um, toward the center of curvature, and let's say this is the center of curvature, think of this thing being a part of a circle. So, this is the center of curvature. Toward the center of curvature, um, the material contracts, and away from the center of curvature, the material lengthens. And the effect of that is that, well, let me, okay, during deformation. So, as you move toward the center of curvature from the neutral axis, points are in compression along the x-axis. And as you move away from the center of curvature, starting at the neutral axis, points are in tension along the x-axis. And so the formula that we're going to use for stresses due to bending moments are that sigma xx, it might be a little surprising that bending only affects the x normal stress, again, like it did in tension compression, but it does, and it's just because of that lengthening and shortening effect. Sigma xx is equal to negative bending moment times y divided by I. And I'll tell you what these things mean, and we'll have to define that I. So y is the height of the point of interest or the desired point above the neutral axis. And so if you're looking at a point below the neutral axis, then y is negative. So below the neutral axis is negative. And I is called the area moment of inertia. So this is the thing for the people taking dynamics right now. This is the one that can be very confusing. We use the capital I, we call it the moment of inertia. It looks just like the mass moment of inertia, but it's a different thing. So this is the area moment of inertia. And you can think of it as how well the geometric shape of the cross section resists bending. Okay, so I'm going to have to carefully define the neutral axis, carefully define I, and then we'll be able to just use our internal bending moment calculations to figure out this stress. Let me say something intuitively about the meaning of the area moment of inertia. So think about this as your beam, okay? And your cross section is this. It's like very narrow in one dimension and relatively very long in another dimension, okay? So this is the side of the beam. This is the front of the beam. And we can have this beam oriented two ways. So this is the side of the beam, but we could have it oriented like this and ask how well this shape, cross-sectional shape resists bending, or we could orient it like this and ask how this cross-sectional shape resists bending. This way, you can, it doesn't resist bending barely at all. Okay, so this should have a very low area moment of inertia if your cross-section is very wide and very stubby top to bottom. Okay. This relatively should have a much better one because it's really hard to bend this thing this way. I didn't change anything about the material. I just changed the cross-sectional shape that had to deal with the amount of bending I'm applying to it. Okay, so that's the kind of thing I'm talking about when I talk about the area moment of inertia. That's what we want to quantify.
Low I means easy to bend.
Low I means easy to bend, correct? And big I means hard to bend.
Would that be in Newton?
It is in meters to the third power, I think. It just has to do with the shape, so it's all just length dimensions. Um, and so if you look at this formula, yeah, like if you have a big value of the moment of inertia, then for a given bending moment, it'll be a relatively low stress. Okay. If you have a small value of area moment of inertia for um, for a given bending moment, you'll have a really big value of the stress. Okay. So let me first define the neutral axis. So if our beam is like this, find the centroid of the cross section, and we will define our coordinate system origin as being at the centroid. And here's our coordinate system. And our neutral axis, which is really a plane, will be parallel to the z-axis, or I guess it'll be the xz plane, and it'll go right through the origin or right through the centroid of the cross section. So this neutral axis, I'm going to put axis in quotations because it's really a plane, is the xz plane, and it intersects the centroid of the cross section. Um, and then the area moment of inertia has an integral definition that, again, like in dynamics, we're not going to use this definition, but you should see it once, I guess. And that is, so we'll call it capital I sub A, and it's equal to the integral over the whole cross-sectional area of y squared dA, where y is the height above the axis A. In our case, that's going to always refer to the neutral axis of the shape. So let me give you three formulas for these. So area moments of inertia For simple shapes, about their neutral axis. The first one is a rectangle. And remember, these are all cross sections. So this is a rectangular cross section for your beam. So if you have a height h, and a base b, the neutral axis is this. It goes through the centroid. So this is our axis A. Then the moment of inertia about A is equal to 1/12 times the base times the height cubed. Uh, and this one, actually, you can see the example that I gave of how hard is it to bend this piece of paper when it's horizontal like this versus vertical. You can see that this is easy to flex when the height is really small, and it's hard when the height is big. And you can see that in the formula, that height is way more important than the base in producing this moment of inertia. The second one is a circular cross section. Um, and we're going to define it in terms of this radius r. The neutral axis looks like this. And so that's the axis that we're calculating this about. And the area moment of inertia about that red axis is pi radius to the fourth over 4. And then the last one is an isosceles triangle. It has to be isosceles because of the symmetry requirement. So it has to look something like this. The two diagonal sides need to be the same length. The centroid is a third of the way up. The neutral axis looks like this. And the area moment of inertia is base times height to the third over 36. And those all just come from, slightly clever application of the integral definition. This is also a cross section. Okay, so remember that this area moment of inertia is not the same as the mass moment of inertia from dynamics, even though a lot of things about it look similar. This tells you something about how the shape of the cross section resists bending. And also, what if you didn't want to do your calculation about the neutral axis of that shape. Like say, for example, that we were building up a complicated shape from a bunch of these simple shapes. How would you do that? Well, you do it with a parallel axis theorem that looks very similar to the parallel axis theorem for the mass moment of inertia. And I'll talk about that next time. Anybody have any questions? That's a lot of just information and writing and stuff. Pretty soon we'll get to some calculations.
Would there be ellipses, like or?
Yeah, I mean, you could do it for any shape. I just gave you the ones that we need for this class. Okay, that's all.